It's another lemma, so you can feel excited again. It's another lemma. It says this. If you take a set of points, n points in real numbers, and you construct Lagrange polynomials. If you construct the Lagrange polynomials of order n polynomials altogether, each of them will be a polynomial. It's a typo actually. It should be a polynomial of degree n take 1. It's a polynomial of degree n take 1. So if you construct your Lagrange polynomials, the lemma claims that these polynomials, as vectors, they are linearly independent. It's the last thing we're going to discuss today. It's a very short proof based on the properties of Lagrange polynomials. It's almost elementary proof. I mean, it's almost straight. It's a straightforward proof. It's not elementary proof. Look, if you prove something is linearly independent, you always follow the same path. You take a linear combination with some unknown coefficients. Here's my linear combination with the coefficients lambda 1, lambda 2, and all the way to lambda n. You equate this to zero vector. But in case of polynomials, zero vector, it's a zero polynomial. So it's a polynomial which is identically zero. And if you want to conclude that something is linearly independent set, your job is to, just from this identity alone, conclude that each individual coefficient is necessarily zero. That's the actual substance of the proof. Well, here, such a conclusion, it will use the properties, these fundamental properties of Lagrange polynomials, that each of them individually returns 1 on one of the points in the set and 0 on any other point of the set. So look what I'm going to say. If I do a substitution, if I sub in the value x equal x1 into this expression, what that will give me? On the left-hand side, this factor will be 1. All of the other factors here will be 0 because of the properties of the Lagrange polynomial. So the left-hand side simply becomes lambda 1. And the right-hand side, if you sub in whatever you want into 0 polynomial, it's simply 0. And that's why I conclude that lambda 1 is 0, by just subbing x1 into that. It's a very powerful method when you discuss a linear independence of functions. Substitution, I mean. If I sub in x2 value, then what do I have? In this left-hand side, every Lagrange polynomial except for the second one will vanish. The second one will deliver value 1. So left-hand side will be lambda 2. Right-hand side will be 0. 0 value of my 0 polynomial. And substitutions like this, and I conclude that every individual coefficient is 0. And that's the end of the proof.